started. And there we have it. You should all be able to see our beautiful Department of Physics. I always enjoy sharing this. We've got a combination of the physics buildings in Oxford and some of the work that our physics department is involved in, including thin solar cells, astrophysics research, particle physics research, and theoretical physics research. But let's move on. So, before we jump in with our second study focus session, I'm going to give a quick introduction to the course and to the PAT itself. I won't be answering any questions at the moment, so anything that comes through I'll deal with afterwards, but I will make time at the end of the session if I can. And don't forget, we have an extended webinar when we come to our final session in October, and that'll give you loads of extra time to ask those remaining questions. I repeat this quick introduction each week for new joiners to the course. If you've heard it before, you've got 3 minutes to go and get yourself a cup of tea and settle in. First things first. The PAT is the Physics Admissions Test at Oxford University, and it is the required test for all candidates applying for physics, physics and philosophy, engineering and materials science. The result which you get on your PAT forms just part of the information which admissions tutors use to decide who to shortlist for interview, but it is a very important part of that information. In order to sit the PAT, you must register as a candidate. Your school do not do this for you. The PAT this year will be on screen and entirely multiple choice, as was the case in 2024. We've worked really hard behind the scenes to make sure that we can gain as much information as possible from this format and to make sure that it is equal in difficulty to previous years and fair to everyone involved. The on-screen test involves a built-in on-screen calculator, which just looks exactly like a regular calculator and works in the same way. There's a practice version of this available, which I'll show in a few minutes, and which I also share in all of our emails. This webinar is part of our Preparing for the PAT course, and we run this course in the physics department on behalf of all those subjects who require the PAT. This course is a set of 8 webinars along with problem sets and summer assignments, and we hope to provide you through this with all the information that you need to take the PAT, to be confident at going into interviews if you're shortlisted, and to feel ready for the content and format of the test. The timetable on screen at the moment is part of the timetable which is at the bottom of every single PAT email, and it's always highlighted in yellow with where we are so that you can follow our progress. You can see that today this is our second study focus. It's a teacher-led problem-solving webinar focusing on optics. In each session, I will make sure I update you on any news or key dates, and all of the information about our course goes on this, the course materials page. This is what our page looked like this morning. At the top, we have our introduction to physics problem solving, and that has some general hints and tips, which Rachel took you through in the first webinar. It also then underneath has all the links which you might need. So you can see, for example, that last week's webinar, the recording of it is there. The link to the problems that we'll be looking at today is under webinar 3, and tomorrow morning I will upload the recording and problems to solve in advance of the next webinar. Finally, a quick reminder that this link on our page can be found from our main Oxford University website, and it contains all of the information about the PAT that both you and your school might need. I share this link in every email, and I will share it again tomorrow morning. It's the most up-to-date page, and it's the one to check for any information that you need. It also has a really useful FAQ page that's got pretty much everything anyone has ever asked. Some key facts for you to finish up. Remember that all tests this year, as was the case last year, will be sat at a Pearson Test Centre, and that applies whether you are sitting a test in the UK or internationally. We've got venues in almost every country around the world, and when you select a test centre, you're able to select a centre which is most convenient to you. That might not be in your hometown, you might be on holiday at the time, gives you a chance to explore a lesser known part of a foreign city. For some people, you may need to travel a little, but hopefully not too much, particularly because we've now got the PAT running over 2 days. And the arrangement that we have here is really similar to tests like the LNAT, the BMAT, the ESAT, and any of the Cambridge admissions tests as well. The PAT is completely free to register for and to sit. And if you are eligible for any access arrangements, such as extra time, you can apply for them when you register. So we encourage you to register nice and early so that we can get everything in place that you might need, particularly if you need something more complex than just extra time. Registration is actually already open. It opened last week on the 18th of June, and it will remain open until the 19th of September. Actually choosing a test date is a second process, and that opens on the 18th of August and will open until the 26th of September. The PAT dates for this year are the 22nd and the 23rd of October. That may fall in a school holiday for some of you, so make sure you are planning for that in advance. The test format that I mentioned is new. It was new last year, but the questions are really similar to questions that we have had since the syllabus last changed back in 2018. We've now had the same syllabus for quite a long time. That means that all of our past papers are absolutely valid, and then in combination with this practice test format, you will be ready to go. A little bit later in the PAT course, I will share a video about best practice at using that test format, just to help you get the very most out of that online test platform. But that is my quick PAT introduction and update. Those of you who have heard it before and were away having a nap for 3 minutes, it's time to wake back up, because I'm going to stop sharing my screen and hand over to our lovely Rachel for our study focus session number 2. Rachel, good evening. Thank you so much for joining us again.
Thanks so much, Kat, and thanks for those reminders. I'll start sharing my screen, and we will begin the session. So Kat has actually emailed the problems for this session. So you are, oh, sorry, I just lost my share. You are welcome to look at those problems if you want to see, just double check the problem on the screen at any point. And of course, at the end of those packs, there are answers. There's even hints just before that. But obviously, the purpose of this session is to practice live your problem solving. So don't jump to the hints. Do not go to the answers, just like I would tell my students, because you're not going to learn during this session if you jump to those. So this is all about problem solving in the moment. So make sure you have some rough paper in front of you and a calculator, because just like in the real PAT, you'll have a whiteboard and you'll have a digital online calculator. But that's what you need to practice today. And actually, our first question is a problem-solving question. In the chat, I think Kat will have adjusted it in a second. I'll be able to see your answers and no one else will. So if you think you've got an answer to something, pop it in there. I can't give everyone feedback, but it gives me a general idea of how people are doing. And remember my rule from last session. If you have a question about my problems or about the PAT, that goes in the Q&A. No questions in the chat, because otherwise we'll lose track. There's so many of you, which is great to see. Thank you very much.
Lovely. In that case, Rachel, I am just about to switch my camera off. Everyone, I have shared the direct link to Rachel's problem set, and I have shared the indirect link to the course materials page. I am about to switch the chat to hosts and panelists only, which means that while Rachel is presenting, you will be able to chat to myself and Rachel, but you will not be able to chat to each other and give any spoilers to the questions. Rachel, that should have given you enough time to get your screen sorted as well.
Brilliant.
I'll be in the background.
Fantastic. I think hopefully I've got my correct screen on at the moment, but let me know otherwise, Kat. I should have my PowerPoint there. And we have our first question. So these are quite good questions. This is a resource called oh, my mind's gone blank. Hold on a second. Next time questions is literally on the screen. Long day. And these are really useful. Your physics teachers might have used them, but you can go and find these online, and they are really helpful in terms of problem solving. So have a little read of that question, and when you're happy, put an answer, just A, B, C, D, or E, into the chat. Even better if you can give me some reasoning. So we've got one answer straight away becoming quite popular. I'm not going to tell you what it is yet. Oh, great participation. Thank you so much, everyone. There's actually two answers standing out as the most popular right now. So we are split in two. Well done, really good participation. Remember, the Q&A is just for questions. Answers can go in the chat. So that's two different buttons on Zoom. Really good participation. Well done. Someone's mentioned the keywords of the session, angle of incidence and angle of reflection. Thank you so much for that. We'll be talking about those. Okay, so to let you know the feedback from everyone, most people are torn between answer B and answer E. Okay, so we definitely seem to be a few more of us on one of those answers than the other. And I'll do the big reveal. So there's lots of different topics and next time questions. These are published online. Great drawings as well. And the correct answer was actually B in terms of half your height. So this is a question all about the law of reflection. As you can see in the explanation here, I'll just have my little laser pointer on for now. If you look halfway down the plane mirror, you'll actually see your toes. So that's if it is directly in front of you. And if you look at parts of the mirror below the halfway mark, you'll actually see the floor, but not yourself. And then if you look straight ahead, this bit seems most natural, you will see your eyes. And if you look at a distance halfway from your eyes to the top of your head, you'll see the top of your head. So that is using the law of reflection, the idea that the angle of incidence has to equal the angle of reflection. And you don't see your image in parts of the mirror above, halfway up, and halfway down. So we need a mirror that is half of our height. And it does need to, there are a few caveats to this, but as in any problem solving, we are making a few assumptions. If it's going to be half our height, we do need to hang the mirror in line with our eyes. But the length only needs to be half of our height to be able to see our full selves. Interestingly, loads of you said E, completely understand why. But actually, the distance that a person stands from the mirror will not affect the amount of mirror that the person needs, so the length of the mirror, to see their image. So actually, if you next time there's a half length or full length mirror near you, play around with that. Physics in real life, you actually only need that mirror to be half of your height. So this is quite a good next time question in terms of problem solving. There's a really good explanation as well on physicsclassroom.com that I've noticed in the past. I use this question with my students. Another question, but read it carefully. In the chat, you could put your answer as above, below, or at. Okay, I'll underline those options, but read it really carefully. And then read it really carefully, because you might have seen questions like this before. Oh, we've got a whole mixture of answers. That's why I like this question. Which element of waves and optics, if you can add into your answer, which element of waves and optics is most relevant in this question? Great, thanks, Finbar. Great, Dan. And really read the question. If you want to change your answer, you can. Oh, this is a hotly contested question. Thank you so much, everyone. Oh, Fabian's changed his mind. Saw your name again. Oh, there's so many of you, it's quite hard to keep track. We're getting a few correct answers now. Well done, Marcus. Okay, I'm going to rule out above. That might change everything for you. Above is an incorrect answer. Read the question again. I think also the image is misleading. Because notice, now I'm going to add one more thing here. This keyword, he's aiming to spear it with a laser. This is what makes this question different to ones you might have commonly seen before. So I know it looks like he has a laser beam coming out of his eye. That is just sort of showing where you would normally see the fish, but he's holding a laser in his hand that he is not using yet. So he can see the fish with his eye, and obviously that is different. The Huey will see the fish above where it is in reality. And when I say see, because that's a virtual image, that his brain is playing tricks on him, your brain can't get its head around refraction. That's why sometimes when you're at a swimming pool will seem a different depth to the actual depth that it is. And that's why you should be very careful jumping into water because of the refraction of light. But actually, he's got a laser beam. And remember, a laser beam is made up of visible light in this case. So well done, lots of people are getting the hang of it because the correct answer is at. He should aim directly at the fish that he sees. Because in the image we saw earlier, that was just showing the path of visible light from the fish to Huey's eye. So yeah, it was a bit of a trick question. That's what can sometimes happen with problem solving. But with the laser, because the laser beam will also refract as it passes from, in the reverse direction, air into water, it will slow down and bend towards the normal. So actually sending the laser beam along that same line of sight where you can see my digital laser right now, he's having to compensate for the refraction of light. And so he should actually aim directly at the fish that he sees. So yeah, it was a tricky question. I'm glad you enjoyed that one. And we're just looking at how that visible light is affected. So we're not too worried about the color of the laser. It's not even stated. All we know is the laser's visible light, and we have the visible light of the fish. All Huey can do is work with the fish that he can see, which is actually a virtual image. And that same light that has been reflected from the fish underwater, refracted, as it leaves water, that is the same path he should end his laser beam. So the light path is reversible and will go from A to B along the same path as it takes from B to A, because we're dealing with visible light here and refraction. So reason we choose waves and optics for this, firstly, mine and Kat's favourite topic. No, that's not the main reason. It's often slightly neglected by our students. And I'll mention where it is in the PAT syllabus, but I know my own students at your age often forget to practice this enough, find some of the keywords challenging, find the construction of ray diagrams quite challenging. But as Kat says, we do really love this topic as well. So we're practicing it today. You need a sheet of paper, you need pencil. I'd have a ruler because we're not drawing scale diagrams, but we need to draw clear diagrams. And I'll be constructing diagrams on my slides sometimes. So you've got to learn your formulae, and the syllabus is clear on that for your PAT topics. Make sure you check your syllabus after this session. Make sure you're happy with it. Keep checking that you're clear on what the syllabus requires, and it's got definitions and equations. Today, always draw your own ray diagram, even if you're given one. So that would be different actually. This has changed a bit because we won't have a paper, if that makes sense. But you'll be able to redraw anything you need to problem solve on your whiteboard. Label your angles really clearly, and I'm going to be doing that throughout the session. Just like my last problem solving session, don't forget simple geometry rules to calculate your angles. So don't forget to draw some triangles, use your angles, etc. And make sure you're happy with Snell's law, and we're going to revise that in a second, and total internal reflection rules. So these are my tips. And also remember, this is a key idea for assumptions in this problem solving. The refractive index of a vacuum is 1. And sometimes we can also say, most of the time, we can also say that unless we're told otherwise, the refractive index of air is also 1. So in terms of the syllabus, these are the relevant parts of the syllabus today. So we're just looking at one sort of key area and key topic. The idea of reflection, angle of incidence, angle of reflection, the idea of refraction. If you're feeling really rusty, quickly write down Snell's law, but otherwise try and test yourself on that today. Elementary properties of prisms and optical fibers and total internal reflection, and often using the idea of the critical angle as a ratio of refractive indexes. So if this is feeling rusty and scary, we're practicing it all today. If you want to write a quick note of anything you can, you could turn it over and only look at it if you really need it in the session, because we're trying to activate our brain and think really hard today. And this idea, qualitative understanding of interference, diffraction, and standing waves. So that means qualitative, being able to explain, problem solve to understand the impact of those effects, essentially, because then you'll have your multiple choice options. So first question is a multiple choice option again, an older PAT question with a prism. Again, read it carefully. And when you think you have an answer, pop A, B, C, or D in the chat there. I'll provide a few hints and annotations. So it is a beam of coloured light, doesn't say what colour. And remember, when we have white light entering a prism, we have that dispersion effect. And why does that happen? Dispersion happens because of refraction. My main tip is always add on a normal at 90 degrees to where that ray is going to hit the prism. Well done, those answers coming in. Fantastic, thank you so much. And then we've got that idea of the beam of coloured light. Oh, I've lost my normal. There it is again. When the light is saying what happens to the light at the prism. So it's not really worried about the other side. It's what's happening here. That's the bit I'm drawing. Okay, loads of answers. Thank you so much. So it's, yeah, read it really carefully. A few realizations in the chat there. It's not about what's happening back in the air again. It's what's happening at the prism. Okay, then think, does that light speed up or slow down? That's the impact of refraction. That's the effect of refraction, sorry. Does it bend towards or away from the normal? Think about your physics knowledge of refraction. Draw the normal, draw, and then draw the ray. So doing a quick sketch yourself can help. And well done. Lots of you got this very quickly. So it's about where the ray goes next. I've kind of given away the answer at this point, but well done. The answer is B. Okay. All of the colors of visible light would have exactly that same impact. They would all be bent down. None of them would go upwards. None of them would continue horizontally in this question. So definitely not A, C, or D for any of the other colors. And we're going to have that refraction towards the normal because the key idea of refraction is as we go from a less dense to a more dense medium, the electromagnetic wave will slow down and bend towards the normal if it is away from the normal, has an angle to the normal in the first place. But in this question, we do have that case. So read it carefully. Lots of you are jumping the gun a bit and heading for this air on the right-hand side here, but it was as simple as B. If you're not sure about why it doesn't go up, just make sure that you draw the interface between the air and the glass and draw that ray coming in. If it would carry on a straight line, it would go where my laser beam is right now. But because it's going to slow down, the rule we have to learn is that it also bends towards the normal. And remember, questions in the Q&A. Next question, have a little read. A few references to Pink Floyd with the last question. It's an excellent example and a good way to remember. Annotating the question or writing some keywords on my sheet of paper if I'm not annotating. I'm really thinking about going from a vacuum into a medium at angle theta, and the refracted and partially reflected beams happen to form at a right angle. That is important. So draw a quick sketch before you go straight to it. And my sketch would look like this. I haven't got arrows, I really should have. I'll think about that another day. But this would be my incident ray. Here is my angle theta. There's a partially reflected ray, and that is what happens at any boundary between any medium. We actually will have partial reflection and refraction. We often forget about this partial reflection. And we have angle theta for the reflection because the angle of incidence equals the angle of reflection. And we also have a 90-degree angle between the reflected ray, that's really important, and the refracted ray. Therefore, using angles along a straight line, so the 180-degree rule, depends how you use your terminology, sorry, if that's not quite the right word. This refracted angle here, theta r, And remember, we're using subscripts to really label our work. Theta r plus theta of the angle reflection will be equivalent to 90 degrees because we've got theta plus theta r plus 90 being equal to 180. So where my laser is pointing, that is an 180-degree rotation. And so I can derive that the angle of reflection equals 90 degrees minus theta. That becomes useful. A few people have got to the correct answer. Well done. So we can assume that as we've got a vacuum here, we assume a refractive index of 1, and we have our medium, I've labelled it, and we have Snell's law. So that's why I mentioned it quickly earlier, but if you're struggling to remember it, there it is again. And again, we're assuming we're in a vacuum, so that first n, we're going to start with the material we're in. That's quite a good rule for refraction, and a lot of you have got to the correct answer. Well done. But try and simplify it a bit more. Some of you haven't simplified it as much as you possibly can. So really think about your trig rules. Well done. Just try and keep an eye on the chat as well. Fantastic. So we've got Snell's law. We're going to substitute n equals 1. And we've got our angle of incidence, theta I. I've started to label things a little bit more clearly, equals n. So that's our refractive index of our medium, which is our key. That is what we're trying to find. N, mystery n, the refractive index of our medium, sine theta r. So theta r is in red down here. And I've derived a term for theta r in terms of 90 degrees minus theta. So that's quite a useful rule to remember. Sine of 90 minus theta is equal to cosine theta. Okay, so when I was saying, can you simplify it anymore? Well done, I think most people have now. There's your little trick to help you. So in the end, when I'm changing the subject for n, I have sine theta, which is my angle of incidence, over sine of my angle of refraction, which was 90 minus theta, the same theta. The rule for cosine theta gets substituted, and then it's as simple as n equals tan theta. So well done. Lots of people have probably practiced that derivation before. But the key there is remembering your rules for angles along a straight line, adding to 180, and to remember to use your trig identities and rules as often as you can. Excellent. Right, the next question is a long one. Remember, if you've got any questions, pop them in the Q&A, but I can tell we're all realizing a few things tonight. And if you want to write down Snell's law, we're going to use that quite a few times in the session tonight, then do that now. The next question will be a little bit longer. And again, one of the favorite things that my students at school like to forget is optical fibers. So there are some rules and tricks with optical fibers, but really solving these problems is all linked to laws of refraction and reflection and remembering things about the critical angle. So I'm going to move on to that now. And this is a longer question, so I'll give you time to have a read. The first two are definitions that are highlighted. So try and write your definitions. You need to know your definitions here. You could write them straight down on a sheet of paper. If you want to type them into the chat, you can. Will, good attempt, but try and be a bit more specific. Can you possibly use another set of keywords in your answer? Excellent, well done. So we've got some good definitions coming in. And with the definition for total internal reflection, perhaps include the condition for it to happen. Excellent, well done. I'll give you about 10 more seconds on the definitions. The next part of the question is to derive. Excellent, well done. So have a check of your definition against mine. So total internal reflection, where we have complete reflection of light within a medium, and the condition is stated here, occurs if the angles are greater, sorry, that should be the angle of incidence is greater than the critical angle. So and it can only occur when a light ray passes from a more dense medium to a less dense medium. The other thing I should add to that is, oh, I've just written a note on my other slide. Oh, actually, there's a note I've added for critical angles. Sorry, I'll move on again. Got muddled up between my two slides. Okay, so we've got the definition there for critical angle, and as well, the minimum angle of incidence at which rays undergo total internal reflection. And well done, lots of you did also state that the angle of refraction at that point will be 90 degrees. So at that critical angle, for the angle of incidence, the minimum angle of incidence will be, the angle of refraction will be 90 degrees to the normal. So that will be helpful for when we're drawing diagrams. And if we represent it as a diagram, which can always be helpful to recap things, we can see here that the critical angle is what a ray with an angle of incidence of the critical angle will be refracted at 90 degrees to the normal. And we can count that as total internal reflection because anything above the critical angle, any angle of incidence when we're moving towards the black line and above black ray, this angle of incidence will cause full total internal reflection. So anything at or above the critical angle, we say we have total internal reflection. Okay, so have a little read. We're on to the next part of the question. You've probably done this in your studies, or you will do soon, or you need to look at this independently in terms of the syllabus. So derive an equation relating the critical angle and refractive indices of the two materials. N1 and N2, they give the conditions here where N2 is less than N1. So see if you can have a go at that derivation. Okay, excellent. We've got some good attempts going in the chat bar. Thank you so much. So really think in terms of those diagrams. And for the derivation, make sure you're starting by using Snell's law. That's kind of why I kept emphasizing it earlier. What's the angle of refraction for light when the angle of incidence is equal to the critical angle? I've just mentioned it earlier, and it's clear that lots of you know that. Well done. And make sure you're using your trig rules to try and simplify a little bit. Okay, so we're using Snell's law there. A diagram always helps in terms of this derivation, and I've added on that crucial angle there, the angle of refraction at when the angle of incidence is the critical angle.
Hi, Rachel, just letting you know you've got a couple of questions in the Q&A as well, because I can imagine you've already got the chat open, your own screen open, and the Zoom window open.
That's exactly what's going on.
I thought I'd let you know to open the fourth one as well.
Thank you very much.
Not a problem.
I'll have a little read and sort of keep the question going at the same time.
They're very relevant to what you were saying as well, so
Great.
all good.
So a good question from Colton. And And that's me considering that the angle of reflection, oh, I wonder if I'm like, I think I'm live answering it, I'm not sure, is the angle of the angle of refraction at that point is 90 degrees, because that ray is then being sent along the surface of the optical fiber in this case. Any angle of incidence just above the critical angle would be reflecting. We go straight into reflection rules there. So we're just looking at that sort of changeover point between simple refraction, when you go from across two different density mediums in terms of your light ray, compared to that moment where we go from where we move into total internal reflection at any angles of incidence greater than the critical angle. But we often need to consider a light ray that has an angle of incidence of exactly the critical angle in terms of our problem solving. I think hopefully that helps. Kat, if you want to add anything there. But it's just sort of that real important derivation point of considering angles of incidence at the critical angle. So we often derive a lot at where the angle of incidence is equal to the critical angle at that point.
Yeah, I think we're good. I'll type an answer to the people who you've answered, and if they want any more information, they can come back to us.
Great, thank you very much. So we've got Snell's law, and at the critical angle, the angle of refraction is equal to 90 degrees. Because that ray, that blue dotted one I've got here, is being refracted along the optical fiber. And so we can derive that our critical angle, or sine of our critical angle, is equal to n2 over n1. Okay? Also, total internal reflection, remember, can only occur when a light ray passes from a more dense to a less dense medium. So that's just a reminder to keep remembering that is a condition for total internal refraction as well. Reflection, sorry. Lots of keywords today. And that's why it's important in optical fibers, because an optical fiber, the fiber will be more dense than air, but we're also going to look at examples with cladding as well in a second. So the next part of the question, this is where the cladding gets involved. You can see the final part of the question, once we've derived that, we've got a bit of an intro here. We've usually got two materials, a core and a cladding. And light may only be transmitted along the optical fiber if the incident of light is less than a maximum angle. Okay, I'll let you have a read of that and start your next part of the question. I just need to close the door for a second. Okay, so we have the expression we've derived, and I would recommend redrawing your diagram on your piece of paper if you're working with that right now. And it's really important, this point where the optical fibers contain a core and a cladding, where the refractive index of the core, and it states it up here as well, kind of the principle is labeled, is derived in where we derived the critical angle earlier. The refractive index of the core is greater than the cladding, because that's the only way we'll get total internal reflection along that core. So one principle, when we're learning it at the age you are now, we often sort of draw diagrams of total internal reflection. That doesn't always happen exactly like that with multiple reflections, and we'll actually model it in a simpler way today. But that's only going to happen, a way to remember it, you're only going to have that total internal reflection if the refractive index of the core is greater than the cladding. So just redrawing the entry point is quite helpful here in terms of solving this question. Well done. I've got quite a few answers coming in on the chat. Excellent. I still think more simplification might be possible. So keep having a look and I'll show you a few steps here. Remember, we've got some rules that we can use for trig as well. So we've got that rule that I just mentioned to allow total internal reflection. And we're going to assume that the transmission is maximum, where we've got the incident angle where the ray meets the core cladding at the critical angle. So rather than drawing multiple reflections like I just sketched on there, we're actually going to make a simpler assumption that we can have the maximum transmission of that signal as long as, and it's kind of where the question was leading us, as long as that ray hits the core cladding interface at the critical angle. So that's kind of why the question was asking us to derive those steps. And then using angles in a triangle, sort of sketching out a right angle triangle, that's also helpful to show that this angle of refraction, so that is where I've got refraction. There's a lot going on here. At point B, we are going from air into the core, and that's why the ray is refracting towards the normal, which wasn't in our original diagram. Actually, it wasn't in our original diagram. I'm adding this on. But that angle there will be 90 minus the critical angle, because all of these angles in the triangle add up to 180 degrees, and that's going to come in handy later. So at point A, there's probably multiple routes through this as well. You might have done this a different way. Okay, so lots of answers coming in. Some of them can still be a bit simplified, but we've got a lot on the right track. So well done. I think there is going to be a square root involved from memory eventually. And at B, we just have simple refraction. Snell's law is going to be useful to help solve this. So we've got two different sort of wave effects, optics effects going on. At A, we've got sort of the start of total internal reflection. We've got that refraction at 90 degrees to the normal. But at B, we've got refraction using Snell's law. And I can put in what I know already, that I'm going from air, which we assume to have a refractive index of 1 for a vacuum. And we were talking about in the question that that is the maximum theta. That's what we were trying to derive in the first place. Then we're going into the core, so the refractive index of the core, times sine 90 minus theta, which is the critical angle, sorry. So 90 minus the critical angle. And that's because I've derived that those angles in that triangle add to 180 degrees.
Avi, now I think you've answered these, Rachel, because I've been typing and not particularly listening. So if you have, tell me. But we've got a question asking about the difference between regular density and optical density, which, as we've already confessed, as optics lovers, I thought was a great question. So I thought I'd let you answer that one. And we've also got somebody saying, for part C, are we assuming that the light originally comes from air and that the refractive index is 1? And I was not sure at this point if you were at the cladding stage or not, so I thought I'd ask for clarification.
Great, thanks so much, Kat. So for part C, I'm trying to remember if the question mentions air, but there's air mentioned in the question up here. They are stating air. I think if it's not otherwise stated, you make the assumption that we're in air or a vacuum, because otherwise you would be directly stated where we're starting from in terms of what that material was. Just reading through that question there. So that probably answered that first one. Might need you to add to this, Kat. Just trying to think what the question's stating here, because I haven't had that one for a while, which is excellent. I would answer optical density and normal density as they're being closely related. So the higher the density of the material, it will have a higher optical density, is the phrase, and a higher density material in terms of material density will have a higher refractive index. I don't know if there's a measurement of optical density, Kat. I don't know if you know that. I'm not sure. But refractive index, how light or electromagnetic waves behave in a material, is closely linked to the density of material. But we can give refractive index, it would be a different value for refractive index. Anything to add there, Kat?
No, because I think we'd be going well beyond even the
Yes.
PAT syllabus if we got carried away and started talking about like the number of wavelengths that it does of light travels in one particular medium versus in air. But we've got that kind of comparison feeling going on.
Exactly. So
Yeah.
it's that comparison, and that's how they link. Good. I can see some people in the chat.
Awesome.
Their diagrams as well. So this is why it's so important to draw a really careful diagram. It's not a scale diagram, but make sure you've got your labeling really clear, because some people are noticing errors in probably their angles of the triangle or which angle they've labeled as what. So We're also going to use the trig identity that sine 90 minus theta equals cos theta. That will be handy yet again. So I'm then simplifying. We're still working with Snell's law, but sort of doing a bit of substitution to help us in the long run. So sine theta max therefore equals the refractive index of the core times cosine theta, cosine of the critical angle. And then I'm using another trig identity because sine is going to be more useful because originally at A, which I'll come back to later in a second, I had sine in my derivation for the critical angle, which I'm just looping around with my laser beam. So I'm using another trig identity here to help me, but you might do this in different order. There's multiple routes to solve the same problem. But I'm using that idea of sine squared theta or x, sine squared x plus cos squared x equals 1. And I'm then substituting in terms of cosine theta becoming the square root of 1 minus sine theta. And I can then, because I've then got sine of my critical angle in my equation, I can then substitute in, have a go at that. I've just shown you where it's about to go, but can you simplify as much as possible once you've substituted in my equation for the critical angle at A into this equation now at B. And remember, the purpose is to try and find the maximum angle of incidence that a ray can pass into my optical fiber and still be transmitted to the other end of the optical fiber. So well done, got some answers coming in. You're doing very well at typing some square roots and arc signs into the chat. And if you just finish off that substitution, try and simplify it. And you should end up, I have seen a few as simplified as this, well done. So when you're looking at the multiple choice options, if it were an optics question, if your answer doesn't look like the options given, try and simplify as much as you can. And thank you, Finbar, for the feedback that is so neat, because it is very, very neat derivation in the end. So basically what I'm saying is persevere. If you think you've taken the right direction in a question, try and find ways to simplify your problem, your final answer. A lot of you are leaving quite a lot that you can simplify further in your final answer. So especially where you've got, I think this part here, the refractive index of the core in two different places, can you work through and simplify that final step?
Great. You've just got one question about what exactly they're referring to by the maximum angle
thank
theta
you.
maximum.
I will answer that now. So the maximum angle, I think maybe I'll have to skip back a few moments here, is that light, firstly, it helps that they actually drew it in the diagram. And it states in the question that light may only be transmitted along the optical fiber if the incident angle of the light is less than a maximum angle theta max. So your ray is only going to reach the other end of the optical fiber where my laser beam is right now. If the angle of incidence, so that's that angle between the ray and the normal, is theta max or less. So they're kind of giving you that information in the question. So effectively, theta max is just an angle of incidence, but it's an angle of incidence that will allow my ray to reach the other end. And then we simplified the problem solving. So rather than dealing with multiple reflections like I drew here, you couldn't really model and problem solve that effectively. And I'll talk about it a little bit more in the next question. We're just going to model that as kind of where the question led us, which was that when the ray is passing along with an angle of incidence at A, which is equivalent to the critical angle, we'll get that refraction directly along the edge of the boundary between the core and the cladding. So that was a sort of assumption and simplification that allows that transmission. So hopefully that helped with that question. The last, good question as well. The square roots at the end for Kaylin. If you multiply out n cloud over n core squared, and actually n core is equivalent to n core squared square rooted, if that makes sense, without being able to draw this right now. When you've got two square roots multiplied by each other, you can then multiply them out and you'll end up being able to derive this simplification at the end here. Okay, so maybe towards the end, if you still want me to go through that again, I can draw it out, but it will take a little bit long in right this second. But really good questions. Thank you so much, everybody. So next question, which is on a similar theme, have a little read of this. And as I said, with every question, there are multiple roots. Okay, so with this question here, what we're really looking at in terms of key ideas is we've got the question asking for the minimum angle a ray can bounce at is being controlled by the critical angle. So they're really giving that clue in the question that critical angle is going to be relevant. Okay, so always, as I always say, drawing a diagram is going to be very helpful. And we've also got this keyword, which I think I'll address in a moment, meridional ray. It tells you in the question it's one which bounces off the wall of the fibre yet stays in a single plane. So, calculating the maximum path length for the meridional ray, light is going to reflect inside the core due to total internal reflection. And the longest possible path happens when the ray bounces at the minimum allowed angle. So the longest path you're going to get, and which is the maximum path length, will occur when the ray is traveling at an angle of incidence to the core cladding boundary of the critical angle. Kind of explained in the question because it says in this underlined section, the minimum angle a ray can bounce at is controlled by the critical angle. So lots of people, when they look at an optical fibre question, want to start drawing multiple reflections along the whole length of it. But instead, we can just model the path as one long triangle where the light hits the core cladding boundary at the critical angle. That's going to give the maximum possible path. So that's what we actually did in the last question. It's actually a simplifying model that gives us the longest realistic path. And eventually in the question, if we go back to the purpose, we want to end up comparing that in terms of time difference to this ray and a ray which passes straight through. So some rays will just pass straight through the middle of the optical fibre, and that's what we'll look at in part B. So those are the most two extreme. But we're really looking at, not necessarily, so I'm just going to answer Evie's question. Firstly, we can't really model a ray that reflects multiple times on this optical fibre. I don't think there's really a way we can solve this problem in this question for that. But also, this ray that is hitting the cladding core interface at the critical angle will travel. I haven't sort of shown it entering the optical fibre. It's travelled a long way to reach that point, and that ends up being a large distance in the end. I'm sure there's a way to model and compare them both, but that is sort of some of the assumptions we can make in this question to solve it. So I've got a few answers coming in. Well done. But if you're with me, stick with me and let's look at what we should do next. So our next step, we're really going to look at making sure we can, oh, sorry, just dropped my water bottle. We can look at the refractive indices. So we can make that assumption in terms of the critical angle and the refractive indices, and we can look at the critical angle between those two. Okay, just going to shut the window. Hold on a second. Okay, so we're using the refractive indices that were given in the question. Again, we've got that core with a really high refractive index, well, a higher, sorry, not really high, compared to the cladding. So cladding is outside, a bit like cladding of a house. That's quite a helpful way to remember. It's around the outside of the optical fiber. And modeling that in terms of a triangle. So we're just looking at a triangle with the critical angle being at the top here. We can solve that the critical angle is 85.81 degrees. And keep as many significant figures as you can in your working, because that is not the final answer. We're trying to find the maximum path length. The length of the optical fiber is 1 kilometer. Okay, it's 1 kilometer. And the extra length, because we're modeling it again, let me just go back to that point as well. The maximum path length, we're really thinking about the ray hitting the core cladding boundary right near the end of the optical fiber. So it's traveling sort of all the way from where it enters the optical fiber all the way to, the far end of the 1 kilometer optical fiber, and then refracting along that optical fiber. So the extra length compared to the 1 kilometer along horizontally, the straight line, the extra length is therefore the hypotenuse of this, because we're modeling it as the incident ray traveling along the critical angle to give us that maximum difference in length. We're making that assumption that's the longest difference in length we can have. So hopefully that is answering Maya's question there. Okay, so we've got that 85.81 degrees. And most of you in the chat, well done, are getting this maximum path length at that point. So we're using sine because we've got our opposite length as 1 kilometer. I haven't changed my units there, I'm just working in kilometers, but you totally can work in meters. My hypotenuse is my extra length. And so the maximum length, this is not the difference in length, this is just the maximum length, will be 1.00267 kilometers. And well done, I can see a lot of those answers coming in the chat. Okay, got a question about the length of the optical fiber, but the length of the optical fiber is given in the question. At the end, we've got the length 1 kilometer, and so that's why we need to use that here. And make sure you keep your significant figures, because obviously with any question with part A, we probably need to use part B. Use that answer in the next part of the question or the one after that. Okay. And yeah, be careful. A few comments in the chat about getting a bit confused in terms of trigonometry, whether they're dealing with cosine or sine. Did you draw a diagram is my question. And did you label your adjacent, opposite and hypotenuse? So be careful in terms of diagram drawing. So part B, once you've got to that answer, and I'll read a few questions while you're reading the next question. Part B is on the board, I'm very used to teaching, is on the screen now. Have a little read while I read a few questions.
Yes, I was busy looking up something for somebody else, and when I looked up, suddenly there were 9 questions for you.
Right. I think the main question is always the question I get at this point. I don't know if Kat, you want to add in anything as well. So this might cover a few of the answers. So Adam and Emma, people are asking about treating it as multiple reflections, but what do we actually have in this question that we can model and then calculate in terms of multiple reflections? For example, I'm just thinking we don't have the width of the optical fiber, we only have the length. And so the assumption we've made is a good one. We're assuming that the maximum path length will be where the angle of incidence is the critical angle, and that ray is hitting the core cladding boundary at the far end of the optical fiber. So I don't just mean like halfway along, but the full length of the optical fiber. And I think you have to go with the information you've got in the question. How can you model it there? But no, this is always the thing that everyone finds a bit challenging with this
Yeah,
question.
I think you had at least 8 of those questions were all about that longest path. So I've ticked them all off as answer live now, but if you still need any more clarification, do come back to us.
Great, we've got some time differences coming in. So I'll go back to that. Oh, someone's asked about staying in a single plane. In terms of that, so that's the meridional ray. So a meridional ray passes through the axis of an optical fiber. So it's going to pass through, it's passing like at least from the lower down through the middle of the optical fiber, but it also means it's not being reflected or traveling in the X or in the Y and Z planes, if we think about it like that. If we think about life in 3D, it's only going to have a change in direction in one plane, I think would probably be the simplest way of answering that, Fabian. Good question. And I might go back one moment for Matilda. So I'll just go back on my slides one more time. So we're just using trigonometry here, where I've drawn my triangle, which with the critical angle at the top here, my opposite was my full length of my optical fiber, and my hypotenuse is the extra length that I'm eventually trying to calculate, x, let's call it. So that means I've got my opposite, I want to find my hypotenuse, and that's why I'm using sine of the critical angle is my opposite length over my hypotenuse. So hopefully that helps explain why I'm using sine. And that's because I'm modeling the path of my ray as being, as hitting the core cladding interface where the angle of incidence equals the critical angle. So that's kind of why and that's why we calculated the critical angle in the first place. So good, we've got some time differences coming in. And that is the case of looking at the path difference. So my students often struggle with the idea of path difference and phase difference. We're not talking about phase difference right now, but that is quite useful to revise for your exams. But path difference, we've got the full length was 1 kilometre, and then we just calculated the maximum possible path. That's why we had that in part A. So the path difference is 2.67 meters. That is what we then need to think of in terms of maximum is to use for time difference. Then the final part of the question involves the word rate, and rate is a question that comes up often in science, but definitely in physics. So in terms of time difference, just thinking about it as the path difference or a distance over a speed, and because we're dealing with light, I'm using the letter C for the speed of light. Well done, lots of answers coming in. The time difference is the first step, and then think about rate of information sending. What does the word rate mean? Now, refractive index and speed are related. Another equation to learn. Refractive index is equivalent to, so the refractive index of a material, I mentioned refractive index earlier, but one way it can be derived for a material is how much does the speed of light get slowed down in that material? So the speed of light in air would be c, and then the speed of light in the material, I've used c subscript s. So it's just a ratio which demonstrates, that's what refractive index is, a ratio which demonstrates kind of how much the light is being slowed down. So if I change the subject, I need to understand what the speed of light is in the material. So this might be the tricky thing where people are stuck for this question if you can't quite work out the time difference. Because you might be happy with the speed of light in air, but remember, we are in the core of an optical fiber now. And that's why they've given you these refractive indices here. So we'll need to use refractive index 1.5, where my laser beam is highlighting right now, to find the refractive index of the core. And once we found the refractive index of the core, using the speed of light, 3 times 10 to the 8, which we need to know, we can then find the time difference because we've got the path difference. We'll have the refractive index of the material the speed of light in the material that's going to be substituted here. And well done, the time difference. Lots of people are getting the correct answer. Some people, I think, just need to check their units for the path difference. Make sure you've converted from kilometers to meters. And well done, some good corrections. Yeah, Marcus and Diva, and I definitely had quite a few good answers before that. Well done. I think some people might have just been using the speed of light. So if you had multiple choice options, one of them probably would be in this kind of question using the speed of light in air. But you have to remember to problem solve for the fact we need to work out the speed of light in the core if we're looking at the time difference across the core. So the final answer then is the path difference divided by the refractive index of the material of the light, sorry, the speed of the light, too many keywords right now, in the core, which I've derived through that definition for refractive index in terms of ratios of the speed of light in air and speed of light in a material. Okay, so got a good question from Evie about the idea of am I looking at, I think, the fiber as a square, because I'm looking at a cross section. So I've not drawn a 3D diagram. And Evie's saying, but they're actually circular in the middle. But we're just looking at the top and bottom surface of the optical fiber. If I drew it as a cross section, so imagine just like cutting it down the middle, and I'm just looking at the top layer and the bottom layer. I'm not modeling it as a circular optical fiber right now. And also I can have optical fibers of different shapes, but I'm just looking at the extreme top and extreme bottom of the optical fiber, I think would be my best explanation there. Okay, so I'll show you the final part. We're now thinking about rate of information that can be sent. And maybe even if you're on that part of the question, can you define what the word rate means or what it means to you in physics or science? So this word rate of information or rate. So really thinking, great, we've got some good ideas from Will, Timothy. Excellent. So I've got lots of people mentioning the idea per unit time. That's really excellent. Well done. You've really got your head around what that means. Because often in physics, we talk about rate of energy transfer, and actually what rate of energy transfer is, or rate of energy dissipation, that's just equivalent to power, because we're thinking about energy transferred per unit time or work done per unit time. So in this question, this is not about power and energy, but this is about sending information, and we're modeling them as square pulses of light. So I used to actually teach a lot more about this. I'm not sure if it comes up in your course, but it doesn't come up in my A-level course at the moment. We're thinking about square pulses of light, and that information is useful because we're thinking about sending information, kind of an on or off situation. So whenever we've got a peak, that we're sending the information, the off is kind of a zero. And because it says it's a square pulses of light, that means the off bit, when there's a gap in information, that is as much time as the on bit. So we are going to have as much time for the on and the off, and we've got that square peak. We can assume the gap will be the same size as a pulse in the square wave. And another important information, so it's saying we need to send information, but we want that information to get there clearly. So to get there clearly, it's kind of thinking qualitatively. We don't want any interference in our signal. A bit like, well, in a very different way, if you had like poor phone reception, you might be getting a bit of interference on the line. So we need to make sure we're thinking about rate as being per unit time. And you can't send a new pulse until the slowest pulse from the previous bit or bit of information has arrived, or the pulses would overlap and corrupt the data. So that idea of that bit of interference going on in the signal. So that is probably kind of the hardest conceptual part of the question, just really trying to apply our knowledge to rate. So really, that's why we just worked out the time difference, because we're looking at the two extremes. Yes, there might be other paths that the ray takes, but we're saying that either the most extreme differences in the rays are, if I go back to my triangle, either passing directly along the middle of the optical fiber, 1 kilometer, or the meridional ray, but the one that travels and hits the edge of the optical fiber at the critical angle. So those are the two extremes, and they have the time difference that we've just calculated. So those are the extremes we need to consider in the maximum rate of information. Okay, so the maximum rate, therefore, will be 1, because we're thinking about how many per second. I'm using 1 second as what I'm calculating for my rate. And the maximum rate, therefore, because I don't want those two different versions, different paths to interfere and overlap and corrupt the data, I end up with 7.49 times 10 to the 7 per second. So well done, some correct answers there. Well done thinking about the idea of rate. Okay, and Matilda's just asked about sending those pulses and the rate, because the question tells you we're using square pulses of light. So just drawing a quick diagram of what that means, rather than sending a wave that could have any value, we're sending square pulses where the information is kind of kind of sending that information, and it's not sending it down here in a trough. So a square wave instead of a sort of transverse wave shape. And we're either going to send the two extremes we've been looking at are directly along the middle of the optical fiber, or towards the edge of the optical fiber at the core cladding boundary. And that idea of having that in terms of being the longest possible path. So those are the two extremes. We can't have information from those two paths arriving at an overlapping time, because the information then won't be clear. Okay, the data will be corrupted. Optical fibers, we're using them for our internet, we're using them to send signals. So we need clear signals. We can't have them overlapping. So the most you can send per second, we need to have a gap of that time difference for the maximum rate we can send those signals. So that's why we do 1 divided by that time differences. And that's exactly what we're assuming, Marcus, the idea that each sort of on part of the signal is, we want to have each of the gaps in those signals being as a maximum, being as a minimum value, that time difference between the two path lengths, because otherwise the signals will interfere when they get to their destination. Okay, I'm going to put the next question up because a lot of students are happy with that question, and one quite fun question to finish on. Have a good read, and I recommend straight away drawing your own diagram. I'll try and type a few answers to the questions I can, and maybe address some last ones at the end. So sketch your own diagram, and notice at the end here, it's a bit fuzzy, but A is equal to alpha. So they do give you that A is equal to alpha, and they also give you the two plane mirrors have angle 2 alpha between them, but I've drawn that as 2 different alphas with a horizontal line between them. Okay, so I'll add some hints, just typing some answers as well at the same time in the Q&A. So, oh, where have we gone? So just labeling some information from the question, A equals alpha, and we can see, because we've got a mirror, when that ray after A hits the mirror, the law of reflection has to be obeyed. So this is a question all about reflection. So straight away we can derive that B is actually equal to alpha. So straight away I've determined angle B. But we need to think about how we're going to derive C and D next. And I would recommend drawing your own diagram. So I'll show you my next step of the diagram. I'm going to focus in on this part here, as you can see on the board, and I would redraw just that part perhaps, but I'll leave the whole thing on the board one more time. Remember, any questions, go in the Q&A. Remember, every answer, so Evie, thanks for your contribution in the chat. Every answer will be in terms of alpha, okay? So not in terms of a value. So I'll show you my next steps for everyone. Oh, got too many screens open. My next steps here, to derive D and C, I've got 3 angles there. I haven't labeled that middle one where my laser is, but I've got 3 angles there along a 180-degree line. So those 3 angles will add to 180 degrees. And also, because I've got a triangle here where E and B are, this angle here, where I've labeled in green, will also be 180 degrees minus E minus alpha, because B is alpha. You might do it a different way, but this is one way I'm suggesting. Again, I mentioned it too soon, I jumped ahead, but along the straight line, C plus D plus what I've just derived in green, that's why I've tried to color code this slide. All of those 3 angles, DC plus this green one, equal 180 degrees. And actually, I can simplify that to a term in terms of, an equation, sorry, in terms of C, D, and E for alpha. I'm going to call that equation 1, so you know which one I'm talking about. Now look at the final bit of the diagram, and I realize I took it off the board, but there is the left-hand end of the mirror cone. And think about your simple geometry rules. So again, we've got a triangle. What could you do with that? Well done. Some people give me some answers. You're seeing the pattern. Well done. Okay. And in that triangle, you should end up with 2 alpha, which we've got in the cone, plus D. And here we'll have angles along this straight line here. Don't worry about this little reflection right now. We're just going to model this as 180 degrees minus E. All of those add up to 180 degrees. And then we've got a second equation in terms of alpha, D, and E. So 2 alpha plus D equals E. So then we can do a substitution. I can substitute equation 2 into equation 1 to find C, because I can immediately eliminate E. I'm substituting via elimination, or you might use other methods of substitution or simultaneous equations. And I end up seeing lots of people saying this, C equals 3 alpha, well done. And then we might notice, because C equals 3 alpha and I've got reflection along the CD line, that's reflection. Again, still kind of considering the law of reflection, D will actually also be 3 alpha. So well done, lots of people saying that in the chat, really good to see. And we're going to use that with equation 2, or you might use a different route. You could use equation 1, but in equation 2, then my only unknown becomes E, sorry. So I can immediately find E, which is 5 alpha. So quite nice dealing with our triangles and straight lines. All the angles in triangle adding to 180 degrees. All of my angles along a straight line adding to 180 degrees again. And then you can have a look at part B. So what happens, explaining what happens after several reflections of the light down the mirror funnel. Whereas in C, we bring in a value for alpha. So have a little think, what happens after several reflections down the mirror funnel? I'm just having a look at your questions now.
Yeah, I think you've got one or two to go back to, just about that previous one. And while you're doing those, Rachel, though, I will say to everyone, remember this is not the only time you can watch Rachel taking you through this. So tomorrow morning, I'm going to share the recording. And what I'd say for those of you who are a bit unsure about the details, go back through the recording and absolutely have a look. And remember, I will share the solutions to these problems further on in the course. At the moment, we've only got the hints on the page. Some of you might have discovered the secret location of the solutions, but I'm not sharing in advance. But yeah, you'll be able to watch this video back and you'll be able to sort of zoom in and watch those sections again and again, and hopefully that'll help you out as well.
Yeah, really good advice from Kat, because the whole point of this summer is to practice your problem solving. So definitely revisit this video, revisit the pack, and that's what the summer is for in terms of practice. You're doing really, really well. Really impressed with this group.
I always think it's a really good sign when we get lots of questions because it means people are really thinking
Yes,
and figuring it out rather than just sitting watching us.
excellent. Well done. So I've got lots of people in the chat stating an answer. Oh, sorry, they can see the Isle of Wight there. So there we go. Well done for part B. It is that idea. And I just sort of drawn this on. I wouldn't necessarily follow exactly this path, but eventually we're going to have reflections back out of the cone again. And you may have considered this before. So it reflects out of the plane mirrors eventually, and that's going to link to part C actually. So if alpha is 10 degrees, this now links back to part A. And we've got all these values for A, B, C, D, and E in terms of alpha. We need to think about this pattern. So this is a bit of a pattern we've got, and I'll go back to the Q&A in a second and try and type some more answers. What is the total number of reflections between the mirrors that would be made by a beam of light entering parallel to the axis of symmetry as shown? Okay, so we're entering just along, as you can see in the diagram there. Well done, I've got lots of people typing answers, so I wonder what you're thinking. We've got that 10 degrees. And I've sort of put two values straight away. So if A is 10 degrees, C is 30 degrees. Got some, I'm just counting, that's not a squared. So that's two reflections I've got there. And then E therefore is 50 degrees. Well done, I've got some good logic. Now don't guess, think about what happens next. So we've got A is 10 degrees, C is 30 degrees. Okay, some really good responses. So yeah, you can start to make some predictions. So our fourth, from that pattern, from that trend, our fourth reflection will have a 70-degree angle. And then our fifth one, this is where the magic happens, will reflect at 90 degrees to the surface. And I've just done a quick sketch. This is not to scale. So at 90 degrees to the surface, that then means our beam will travel in it back in exactly the same way it just was incident on that surface. So incident along the normal and reflected along the normal to that surface. Remember, a normal is an imaginary line we can draw on any medium where a ray hits it. And the imaginary line, sorry, is at 90 degrees to the surface. That's the key point. So then reflecting back along the same path. So well done. Yep, few realizations. Well done, Ewan. Well done, Will. And a few people said it earlier. Some people went for 7 because I think you thought it would just be one more reflection after the third reflection. But actually, the correct answer is 9 reflections. So well done. Yeah, Evie, well done. Tanishka, excellent. So quite a few people said 9, but quite a fun question in terms of noticing that pattern. They're not going to give you all of the alphas in the diagram. The reflections will continue, but it's just thinking about what's the condition for then the ray to travel back in exactly the same direction it did. And that would be when the angle of incidence is 90 degrees to the surface. That will then start its journey back in the other direction. So, Kat, we might round it off there. I think there's a little bit more in the pack on that question if anyone would like to. I'll put the working for A for someone in the Q&A wanted me to just pop the working for A back on the screen. And I'll try and type a few more answers, trying to decipher a few questions.
Perfect. Thank you so much. I'm going to take the very risky move of switching the chat back on so that you can now chat to everyone. No, we're okay. We're okay. Thank you so much, everyone, for getting so involved. It has been an absolute pleasure. And can I just say, a few of you, every time you pop something into our chat or into a question, say, I'm sorry for asking. Don't be sorry. This is literally what Rachel and I are here for today and what the whole of the Oxford Physics team is here for. We are here to support you in this journey of developing your problem solving skills. And we're so happy to be on this with you. The only thing I have to say is I've had lots of questions today about, yes, but is there just a textbook? Is there a syllabus? Is there a list of every equation? So I thought I would just finish up by saying we are not being deliberately mean to you in Oxford by giving you this quite simple syllabus and not giving you equations. The reason for this is actually because we love physics and we want to meet people who also love physics. So we have a rough idea of what physics we'd like you to know, and then we want you to be able to put it into as many exciting contexts as we can think of. So whenever we give you that answer of, there's not a fixed list, it's because physics doesn't come with a fixed list. But we're taking you through our biggest topics and building these skills so that you can join us on this journey in physics. Thank you so much to everyone. I think we are going to stop the live stream now to stop the recording. I will say goodbye to you all. We will be back next week. Next week, your webinar will be based on solutions from the problem set, which I share tomorrow morning. And it will be hosted by a different member of our physics team, be hosted by our head of outreach, Sean Tadaldi. So you'll get to meet somebody else along with another 3 of our recent graduate and undergraduate students. So we will see you then. I will be in touch tomorrow morning with all of our recordings, problems, and all the usual things. I'll switch the cameras off, but I think Rachel's going to be typing for another minute or 2 as well. So thank you so much, everyone. It's been lovely to see you all. Goodbye for now.